just an example, we're thinking it could be a function of several variables. We could think that's something like, I'm looking at a table here in section 14.1. It's got one of the wind chill table, but we could think of that, the air temperature, right, wind chill index is a function of what? Air temperature, but also what's the other variable? Yeah, the wind speed, right? And that's what we're saying. I mean, we can look at just situations like that as what we're talking about in section 14.1, where we go with functions of several variables. We're saying, okay, the wind chill index would actually give us, okay, that's a temperature based on like the air temperature, but also the wind speed. So many examples in this scenario. So, and we've got a copy of the worksheet just so it makes it easy to work so many problems in class. But I'm going to write one like the first one. We used to do what? Function of x equals x squared plus 2, previous to this section. What letter is f of x?
Y.
Y, okay. But y is only a function of how many variables?
1.
1x, right? So today we're going to see stuff like, well, z equals something like cosine of, I'll write this first one down, what? Cosine of 4x plus y. All right. So now the z is composed of two variables, x and y. Now how can I write the f of x here? The f of x doesn't work. But the notation we can now use is z is a function of x comma y. So we can write z as a function of x and y. This is multivariable functions. We can write z as a function of x and y. And surely we get in the problem we go, something's a function of x and y and w. All right? But that's the notation we now can use. We just put a comma between the two variables that this z is a function of. Okay? Well, to start out with, because we're talking about multivariable functions, this being a function of x and y, we should look at things like domain and range. But always remember, f of x, y, can't you think of f of x comma y as z? Like the z-axis. You can think of this geometrically in all these scenarios. So in this first problem, that's what I want to ask for. Let's express the domain of this function. What's the domain of f? I noticed on this sheet they called it g of x and y, but I'll just keep this f of y. What's the domain of the function f? Previous to multivariable functions, domain, we only thought of x, didn't we? Now domain is what's going on with x and y. What's going on in the xy plane? What's going on with the variables x and y? That's what we're thinking about for domain. So what's going to be range? What's the other letter?
Careful.
Z. Yeah, the z. So when z will be, we're going to be thinking about the range. Thinking like three-dimensionally. But your domain is just what's going on with x and y in the problem. So when you and I got to look at this problem carefully, we know about trig functions, cosine. Domain of f. What is x and y allowed to be? Relationship with x and y in two-dimensional space. Is there a limit to it?
Mm-hmm.
Very good. Can't x and y be anything? Can't you get the cosine of 1,000 degrees and the cosine of 0? That still exists. There's no like weird things in here. So the domain of f is actually, all real values. Now, if you wanted to put the r thing right, you want to do this, then can't we do something like that? Because we're thinking what? All x's and y's are allowed to be. If I graph the x and y values, like make a graph of this, well, we're saying it could be all points, all x and y coordinates, all pairs in two-dimensional space. So wouldn't I be shading everything? This is my domain, and all these points. And that's what we're saying. So it's all x and y, it's all real numbers. Feel free to just do this. The range is a different story. What's the range of this function now? Okay. What do we know about cosine? So now we're thinking about z. Z equals cosine. What's the highest cosine ever gets to?
-1 to 1.
The highest is 1, the lowest is
Negative.
-1. So there's our range. This has a limited range. So the range, we're thinking, what's z allowed to be? But domain was what's going on with x and y in terms of that. You can think of the xy plane. So the range, I'm just going to write -1 to 1. Cool. Well, can we look at another example? And in this time, everyone, we're going to sketch the domain. So let me go to the next problem. It's the function f of xy equals, I've got the natural log of 4 minus x squared minus 4y squared. The directions say, find and sketch the domain. So we don't need the range. They just want the domain. So this is where we start in 14.1. We need to talk about functions of several variables. And we're talking about functions maybe we can graph three-dimensionally. We should be thinking about, well, what's its domain, what's its range? Find and sketch the domain. That's what's going on with x and y, true? So our focus is this. This 4x minus x squared minus 4y squared. So for domain, I'm thinking, all right, what can x and y be? And then we'll sketch it. We'll sketch it in the xy plane. Okay? So for domain, what does x and y be? Anybody know about natural logs in this parentheses?
Greater than
Can
0,
it be
right?
negative? So
No,
it can't be negative. Can it be 0?
no.
It can't be 0, can it? Natural log of 0 is undefined. Right? Hey, keep in mind, because you might see a problem with the square root. Square root can't be negative. Like the square root of -1, that's not real. But can you get the square root of 0?
Mhm.
So yeah, you can get the square root of 0, but you cannot get the natural log of 0. So this is what I'm going to write. For my domain, I'm first going to find it. I'll start with this. Oops. 4 minus x squared minus 4y squared must be greater than 0. I'm not putting an equal sign there because of what we just discussed. But if that was a square root here, you could have put a equal sign. I just wanted to show that to you so you go, oh, a problem with the square root there would be quite similar. Okay, there's my domain. Hey, can we rewrite this? Because it has x's and y's, and just get the constant over here. I'll do that. I'm just going to subtract 4 on both sides. Now, I don't like all those minuses, so I'm going to get rid of all the negative values. So I'm going to multiply -1 on both sides. Do I have to do anything with an inequality?
Yeah, you could change the sign.
Okay, so if I multiply -1 on either side of an inequality, I switch the direction. Sure. So I've got x squared plus 4y squared is less than 4. There's the domain. We just described the domain. There it is. No leeway. That's a written expression of the domain. All x and y coordinates such that x squared plus 4y squared is less than 4. But in this scenario, it's kind of hard to really understand that domain. So that's why we sketch it. They wanted us to sketch this domain. We're going to sketch it in the xy plane. How do I sketch that? Is that a circle?
Yes.
X squared plus y squared equals 4 would be a circle. See, the less than means we'll just shade inside it, whatever this is. Right? We'll just shade inside it. But that's not a circle. X squared plus y squared equals 4 is a perfect circle. Does anybody know what it would be? It's got like a squish circle. What do you call that? An ellipse. And the easiest way to sketch an ellipse, everyone, think of that with an equal sign. The easiest way to sketch an ellipse, I'll put the equal sign now just so we can sketch the actual curve, is the easiest way to sketch this ellipse here is use intercepts. So I'm going to start with x equal to 0. X equals 0, hide that. What's y equal to?
1 plus minus 1
So y can equal 1,
or negative
or
1.
y can equal -1, right? And we get 2 easy points. Now, let y equal 0. What if y is 0?
Plus minus 2.
Also minus 2. Alright. Sketch your ellipse. Curve. And when we're sketching the domain of that multivariable function. of x and y. Where do I shade?
In between.
Because it's less than, I shade inside. There it is. This is negative 2. If you want to label these, that was 1, that's negative 1. It's not a rectangle. Sometimes on tests I get a rectangle. It is not a rectangle. Right? That's the domain. Now if you're curious about the range, I know I didn't ask for that. Natural logs, a range, it could be all reals, couldn't it? Right? But the domain, x and y, couldn't go outside of this. So think of that three-dimensional graph. You're like, oh, it all be kind of squished in there. Okay, anything else I should do because it didn't have the equal sign? Back in your inequality days, what should I do at the edge of that curve? Dot it. So I'm just going to dot it. I'm dot that curve because it didn't have an equal sign. So it's a set of all points inside of this ellipse, but not on the edge of the ellipse. And there's our sketch of the domain. Cool.
There's a positive 2, right? On the
Oh, you're the
x-axis.
best. That little dash makes it look like a negative. Thanks, Art.
Uh-huh.
Negative 2 to 2, negative 1 to 1. Thank you. Excellent. Hey, just so you're curious, because I think I have one line of problems up like this. What if this just had, you know, x plus y plus 1? Well, then the x plus y plus 1 would have to be greater than what? 0, right? Okay. And then you'd have to sketch something like that, right? Well, what does that sketch look like? That's not an ellipse. I heard it's a line. And where do you shade? You shade above the line or underline? It depends. If it's y what? Greater than something, you shade above it. If it's y less than, you shade below it. True?
Mm-hmm.
Just make sure. In that case, you just have a line. Maybe it's going like this. Maybe the line's going like this. But you're shading everything above it, or that would be it for me. Nice. All right. Over now, they want us to do. I mean, we're going to work this problem that I have here. Sketch the graph of these are problems just from section 4.1. 8 minus 2x minus 4y. This is going to become rather important throughout the remainder of this chapter 14 here. Even in chapter 15 and chapter 16. We're going to have to sketch this thing. So first of all, what letter can I call this? I'm not talking about just sketch the domain. We're going to sketch the graph.
Z.
That's z. So you can only say the function of x and y is z. Okay, so I'm going to get ready and put the x-axis, y-axis, z-axis. The positive y-axis. This is the positive x-axis. This is the positive z-axis, right? I do want to point out some students do like to show how, okay, there goes the negative x-axis. They extend that. This is up to you. And there goes what? The negative z-axis. And there goes the negative y-axis. And you just want to put a little bit more into it. A lot of times you'll notice, I'll just go up, for all the positive axes we have. Okay. So z equals 8 minus 2y, 2x, whoops, sorry, minus 4y. I'm going to rewrite this and put the x's and the y's and the z on one side and keep the 8 on the other side. So I'd have 2x plus 4y, if I had 4y on both sides, plus z equals 8. Isn't it the same equation? Does anybody recognize this from the last chapter? What this should be? It's got no x squareds. It's the equation of some surface. That is not an ellipse. Right? Ellipsoid. This is not a sphere. It's not a paraboloid. There's no squares on any one of the x, y's, and z's. That's a flat out what?
Plane.
Plane. That's just a plane, isn't it? Right? If you're curious, that 2, 4, 1 is the normal vector to the plane. Remember that?
Mm-hmm.
So we're going to really be sketching a plane. The easiest way to sketch a plane is by the intercepts. I mean, it's going to look like a triangle. That's what it's going to look like. So I can use these negative y's, x, negative z. I might take this off so you can really kind of focus on it. Let's use the intercept method. So pretend x and y are zeros. What would Z have to be in this problem?
8.
We need 2 more points. I'm getting the intercepts. Like the x-intercept, then the y-intercept, then the z-intercept. Just like I did the ellipse.
So
Cool.
X will be 4.
Pass that back. There you go. In case you want to write on that. All right, what if x is 0, z is 0?
2.
2, 1 more intercept. What if, what's left?
X is left.
And x is up. We're going to plot all these, connect them.
4.
But it will look like a triangle. So if you don't want to have these, that's okay. Like in my setup here, my 3-dimensional graph. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. Put a dot. 1, 2. Put a dot on the y-axis. 1, 2, 3, 4. The reason I raised those negative axes is because I didn't have any negative values here, did I? That's right. Another way. And we just connected. This is just a portion of the plane, but it's a nice sketch of the plane. That's a nice sketch of the plane. That's something you'll do often in this chapter. In the next chapter. Especially chapter 15 and 16. You'll find yourself making sketches like that. Imagine making a solid out of this. Imagine taking that flat plane, that ramp that's coming down there, part of that flat plane, and then putting some sides where the sidewalls are the XY plane, the YZ plane, the XZ plane. You can build a solid out of this. And think of the solid, they call it a tetrahedron. Cool. Is that okay with that? All right. What about this one? We've done this before, but I wanted to do it again. Because this problem is in section 14.1. They said, can you just sketch this? I did this once at the very end of class one day, when we just learned about cylinders. Did you notice what letter is this again? It's only got 2 variables. So what's x? Is x just 0? X can be what? Anything. X can be anything in this scenario. X takes on any value, whereas z is equal to sine of y. But we gotta make a sketch of this. Okay. Let's make a sketch of this. Well, there's the z-axis, there's the y-axis. What's the sine curve do? It goes up and down, as you order them. The z and the y-axis come up, go down, come up, down. Does that work? You want to keep going down here, you can. You go down the negative axis. But x can be anything, so can we ride down this x-axis and make another trace? I'll just connect these. It's just a wave, isn't it? It's just a wave. Like I said, this is stuff I have on the back of my house under the deck to pull water away from the house. And get the downpours like we had earlier this week. Okay. Hey, number 5. So now we're getting into what's called isothermals. And in this image, you just see, they call these level curves. And level curves or isothermals are shown for the water temperature in degrees Celsius. This was Long Lake, Minnesota. And we're saying that the water temperature is a function of depth and time of year. Well, they just want you to estimate the temperature in the lake on day 160. Well, I'll make a sketch of what we see there. X, Y, this is day, this is depth. And they go, can you estimate the temperature on day 160? I notice on the sheet you got a 120 here. Then you have a 160. There's a 200. Can you estimate the temperature on day 160? right? Estimate the temperature on day 160 when the depth is, oh, and please add this to this problem. Can you write on here? Estimate the temperature in the lake on day 160 at a depth of, let's say, 10 meters. Well, they give the meter readings over here to the left. They've got 15 here. They've got 10 here. They've got 5 here. But I mean, these level curves I see going through here, bless you. I see this level curve coming down like this. And what's the number on that level curve? 8? So let's line it up. What's going on at 60 and depth of 10? What do you estimate? You can draw on that piece of paper. What are you estimating as the temperature? Because the level, number 8, I'll notice at this point, everyone, on day 160, at a depth of 10, that this level curve, it looks like it went underneath it that had the 8 on it. And over here, there's a level curve over here, there's a level curve of 12. So how can I estimate that? What would you use? Some number between what? 8 and 12, right? These were the temperatures in Celsius. These are the level curves, and these numbers represent the temperature in Celsius. So something between 8 and 12, but this is closer to the what?
8.
8, what would y'all come up with? I mean, you can just estimate it.
8.5.
8.5, is that appropriate? Yeah, that'll work. You know, so you just say, well, it's not exactly 8, but it's closer to the 8, 8.5, could you use 9? Absolutely. So we're saying, it's roughly around what? 9 degrees Fahrenheit. I mean, no, this was Celsius. So my answer would be, approximately 9 degrees Celsius. That's it. Well, let's talk about these contour maps. And when contour maps are level curves. And there's 3 scenarios given there. Before we do that, I wanted to do an exercise before we look at this contour map. So, I'm going to use the function f of xy equal to the square root of x squared plus y squared. And what letter is this?
Z.
I'm going to put this off to the right, and this is the problem I want us to do. I know it's not in the sheet, but we're going to take a break here and talk about level curves. I want you to sketch 3 level curves. Of the function of x and y. Okay. So the topic right now is level curves, and it's in section 14.1. You know, the level curves can represent what's called a contour map. Level curves are drawn in the xy plane. This is z. This is a 3-dimensional graph, everyone agree? But the level curves are drawn in the xy plane. So, step 1. Let z equal to the constant k. That's the first thing you're going to do. I mean, of course you can use any other constant, but we'll let z equal the constant k. First step, you're going to draw level curves of some function of x and y. Function of x and y is a z. That's a 3-dimensional graph, but they asked you to sketch the level curves of function of x and y. The first thing you're doing is let z equal this constant k. And it's a constant. Alright? Your next step is to write it out. What do you now have? K is equal to, what do you have here? Square root of x squared plus y squared. And we're going to sketch curves in the xy plane. Okay?
So whenever you hear level curve, it should always be xy plane.
Exactly. When you hear level curves, we're thinking xy plane. Level curves. XY plane. I'm going to make sketches in the XY plane. And it'll be level curves. I have to be very, very clear though, Art, and everyone, level curves of a function of x and y. Because later on you might go, well, what if you got to do level something, a function of x and y and z? They might call those level surfaces.
Huh.
Cool? But right now, yep, level curves, a function of x and y, we let z equal k and we draw them in the xy plane. This though, everyone, you're now, step 2 is going to be, now that I wrote this, I let z equal k. You're going to pick k values. For step 2, just pick any k values that you want. 3 simple k values, because you need 3 level curves, and make sketches of these. But I also want to add the word manipulate. Manipulate. You're probably going to want to manipulate your equation. For instance, let's say I'll start out with, what if I let k equal 1? Then what do I have? 1 equals to the square root of x squared plus y squared, right? I don't know how to graph that. That's bugging me. What can I do to both sides? I square both sides, I get 1 equals x squared plus y squared, true? Do you all recognize this? You got to recognize how would you sketch this in the xy plane. And now it's a circle. So for step 2, I know I didn't write it right. I know I didn't write this down, but I will explain it to you. Step 2 is pick k values, but also manipulate this to your liking. Manipulate the equation as something you're familiar with. Like, is it easy to solve for y? I'll isolate y. Maybe they're lines. Maybe they're lines. I'll isolate y. True? But in this case, I solve x squared plus y squared. So I'm going to think, oh, circles. Hey, what is that? A circle with a radius of what?
1.
There's one. Now this is funny. You know what we do with level curves? You saw that isothermals I just showed you 5 minutes ago? Those are level curves. Did you notice there were numbers on those level curves? In real life, those numbers represented the temperature in Celsius, right? We put the k values right on the curve somewhere. Anywhere on the curve. So you can put it right here. You want to write k equals 1? Some mathematicians just put a 1. So if you don't want to write the k equals, you don't have to. But you got to put it something. You got to label it. Because that can represent something in real life, like temperature. Now I do need 2 more circles. Pick a k value, use them small, what, 2? So I want if x squared plus y squared equals 2. I'm going to let k equal 2. Wait a minute. I didn't do that right, did I?
No, it'll be 4.
So I'm thinking, before I even do this, maybe I'll manipulate this. K squared would equal 1. I'm just going to write that, you all agree? So now, if I let k equal 2, now I see what I have. I have x squared plus y squared equals 2 squared. That's a circle with a radius of what? 2. That's a circle with a radius of 2. Draw that. Almost done. I only wanted 3. K equals 2. K equals 2. Or just put a 2. But we always label the k values on our level curves. It's also going to be called a contour map. Right? This is representing some surface, 3-dimensional. Right? In the Army, they do map reading and stuff. Cool. One more. What do you want to let k equal? K equals 3 sounds good to me. What's the equation? X squared plus y squared equals 3 squared is?
9.
9. That's a circle with a radius of
3.
3. K equals 3. Looks like a dartboard, huh? 3 level curves. Now, you're done with the problem. I'm going to extend this. Can you make a rough sketch of this function using your level curves? By the way, you can do this with any multivariable function or function of x and y. I'll go like this. You want to go to negative here, you can. You want to go to negative there, you can. All right? This thing right. Positive y, positive x, positive z. This is what's going on 3-dimensionally. this represents, think of that as a slice of some three-dimensional surface, right? It would be a circle. These are the heights. Those are the z values, three-dimensional. So at a height of 1, I have a circle like this, right? I'm going to make a rough sketch over here. At a height of 2, the circle got what? A little wider, a little bigger. At a height of 3, it got even what? Bigger. That's what I'm going to draw over here. Because they said what? Rough sketch. Make a rough sketch of this. So I'm going to do what? It's equal to 1, it's equal to 2, and it's equal to 3. The circles kept getting what? Bigger. Now be careful. At 1, was it bigger or smaller? It was smaller. Yeah. What's going on at 2? It got bigger, right? This was at z equal to 1. This was at z equal to 2. K values are now z values. And what's going on at z equal to 3?
It got even wider.
It's even wider. But I'm doing it like distorted because it's three-dimensional. Does anybody recognize what we got?
Cone.
What is this surface? This is called a surface. You recognize it from last week? It's a what? It's a cone. It's a circular cone. Don't recognize it? That's a circular cone. But do you see how now we can do this in any function? We're like, oh yeah, that's the circular cone. These are the level curves of the circular cone. They look like dartboards. These are like these slices just cut out at different places. But that's why they use this for map reading. So I pull up the map, I'm like, okay, here it's just, it's getting wider and wider and wider. We got this three-dimensional looking cone here. Cool. So on that note, there are 3 drawings now. And we'll practice this some more, but there's 3 drawings. I'll put these on the board. They wanted you to take each one of these 3 sketches of level curves to make just a rough sketch of what it would look like three-dimensionally. So remember, it doesn't have to be perfect, just a rough sketch using a level curve. I'll erase this, erase this. Let's see, the first one. So we won't sketch 2 level curves. I'll get this out of the way. All right, here come the level curves. Oh, the circles again. When I look at this image here, and they're really what? There's a lot of tight ones here, huh? A lot of circles in here. A lot of circles in there. Then they start widening out. And what's this number right here? 11, then what? 12. But in here they were all really what? Really tight. And then if you count all these numbers in here, this one 11, 12, and what?
13.
13. These are really low. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They're all squeezed in there. But so it was really tight at first, and then it started what? Widening out. Can you give me a sense of what that would look like? So at first it was really what? Really small, really small, really small, really small, really small. It's getting a little bigger. But I get up to what number? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It wasn't until I got here when they started to what? Kind of stretch out like that. So I'm thinking, well, it's not going to be the perfect cone, but it'll be more like something like this. Yellow grid. Maybe something like that. Because these were all so tight together. So it's not like the perfect cone we had before, right? But they kept getting bigger. True? These were really tight together here, really close together, and then they started spreading out more. So that's why I'm like, okay, now it starts to spread out like that. Kind of like a tornado or something. Hey, what's the next one? Skip the second one. That's not good. Can you do, I really want to make sure you can do letter C. I see a bunch of squares. It's like this. It's like this. It's going to help me think about what the heck is this three-dimensional. Well, let me put these numbers down. What was the number here? 2, 1, 0, -1, -2. These are the z values, right? They're k values as level curves, but these are the z values. At a height of 2, you got that. At z equal to 2, that's what it looked like. Little square. Height of 1 is bigger. Height of 0, it's even a bigger square. Height of negative 1 is even a what? Bigger square. Height of negative 2, it's even bigger. We know what's going on here? Starts with a P. Pyramid. Now this is just a pyramid. And that's all you got here. It's like, there's that big thing. You don't even have to label z-axis. It's just going to keep getting what? Each one of these will get smaller, 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 and like, this is a pyramid. Pyramid. Just a rough sketch. You go, do I have to sketch the z-axis? Nope. You're just indicating you have an idea what this would look like three-dimensionally just by looking at level curves. And that's good. That's good. You're able to look at this and think about what is that three-dimensionally? It's a pyramid. It's just a pyramid, right? Well, because between 2 and 1, there's an infinite amount of level curves in it. Cool. Hey, flip that over. Draw a contour map. What do they mean by contour map? Same thing. Draw a contour map. You know what they mean? The level curves. The level curves. What if you deal with like temperature, like we did before in depth? It was like temperature, depth, the one on the previous side. Had day of the year and depth. They call these isothermals. They call these isothermals. But contour maps are just sketches of the level curves. You indicate before it's in the XY plane. Here's the function. You're going to draw a contour map of that function of x and y. So the first step, what do? What do you let z equal? Let z equal k. That's how you draw a contour map. Okay. That's step 1. Step 2, you get the pick k values. Step 2, you get the pick k values. Alright? I'll get started. No one care if I use k for 1? So I'm just picking k values to make these sketches. Daggone it, that's not a circle. That's not an ellipse. What do you call that, a hyperbola? Hyperbola, Alice? Yeah. It's a hyperbola. That's a hyperbola there. So when I am going to sketch this hyperbola, hyperbolas go like this, but sometimes they go like this. And I got this memorized back from pre-calculus. It's not that bad, everyone. Which way these hyperbolas, are they going like this? Down here, or maybe over here? What I do is, I just use an intercept. For instance, can I let x equal to 0? Mm-hmm. So I'm just going to check this out. What would be going on at x equal to 0? See, intercepts get me out of any jam. If x equals 0, right? Then what would y be? I'll put a question mark here.
That becomes a height.
If x equals 0, can I get a point?
Imaginary, yeah.
So nothing's going on at x equals 0. Interesting. Do you all agree? Nothing's going on here. Just put a big what? That can't work, but I do believe we can let y go 0. Let's see about that. What if y equals 0? I do.
Plus or minus.
Okay, now we got points. So now this helps us understand which way these curves are bending. There's a point right here. There's a point right here, negative 1 and 1. These curves are just going to come out like this. Just like that. What about here? Nothing's going on in the y-axis. Now before I forget, do you remember I always label this? What was the k value?
1,
K equaled 1. How about over here? What would k equal?
2.
K equaled 1, right? It's the same curve. Okay, hey, let's pick another k value. How about k equal to negative 1? Now what do I have? And I'm going to rearrange that. Can I multiply negative 1 on both sides?
Mm-hmm.
By golly, it's another hyperbola, isn't it? It's more hyperbolas, huh? I'm going to let k equal negative 1. It's more hyperbolas. Well, let's try the intercept method. Can I let, I'll try it again. Let x equal 0.
Yes.
Ah, works now, works now. What's the y value?
Plus minus 1.
I'm telling you, when it comes to these hyperbolas, ellipses, when you got to make sketches of ellipses and hyperbolas, just use the intercepts. For that previous problem, the three-dimensional sketch of a plane, use the intercept method. Works every time. I'm going to plot those. Right here, and right there. I'm curious, can y equal 0? No.
No.
So this, there we go. Just hyperbolas like this. Now what's the k value? I gotta label this.
Negative 1.
That's good enough. You got it going there. If you use k equal to 2, you would have got more out here. K equals 3. If you use k equal to -2, you would have got another one here, another one here. If you wanted more level curves. But I do want to point out another one. This is cool. What if k equals 0? Sometimes it's fun. You just go, well, what if k was 0? What do you get?
Oh,
Finish
x
this sketch.
squared equals to y squared. X
Now
equals
that's not a hyperbola. Take the square to both sides.
to x equals to y.
Yeah, y would equal plus or minus
X.
what is that? Right.
Straight line.
2 lines. You all agree? Y equals plus or minus x. Y equals x is like that. Y equals negative x like that. There'll be lines that go right through this. And I'm going to do it right now. I think I got enough room to squeeze right through those curves. Here. And then what? Here's the level curves of this thing. Now I got to label these. What was k equal to?
0.
K equals 0. Here. K equals 0. You got it. Nice.
This looks like an asymptote.
Yeah.
Right?
It's neat though. That's what I always can do with this stuff. I want to do number 8 together. So what they want us to do, this is like the one we did earlier. Sketch level curves. Remember, I'm going to use that word manipulate. You might want to manipulate it first. And then we'll think about what does it look like three-dimensionally, okay? By the way, great job with this. So a big portion of section 14.1 is level curves. Do you notice that? I just want to point that out. It's not the whole section, but a major portion of this is level curves of a function of x and y. See, sometimes you'll notice even on my practice set, I'll just go, I want you to ask them to make a sketch. I'll just go, what are the level curves of this? And I'll put answers. Letter A, are they circles? Are they lines? Are they hyperbolas? Are they ellipses? And you'll think about it, maybe make a sketch just to see what it is. So they want you to draw level curves, a contour map of the function of x and y. What is this thing? This thing looks crazy. 100 over 1 plus x squared plus 2y squared. Okay, and by the way, this is real life application. They're talking about this. What is this representing? This is a temperature. I mean, function f was called big letter T. Capital T stood for temperature of a thin metal plate. A thin metal plate located in the xy plane has temperature T of x and y at point x and y. Draw a contour map. They wrote isothermals because it's dealing with temperature. Draw a contour map, isothermals, of the function showing at least 3 level curves. So we're going to draw 3 level curves of this. When we're done though, I was wondering if, once again, can we use this to make a rough sketch of the function of x and y, which in this case was a big T. And we'll do that again. All right, let's start out. Now, level curves, xy plane. Well, the first thing is, step 1, I like z equal 1. Okay, yeah, there's my z. Let z equal k is my first step before I get lost with level curves. So let z equal k, I get k equals 100 over 1 plus x squared plus 2y squared. Here's my recommendation though. I didn't write it on the board, but I go step 2, oh, you just got to pick k values and make the sketches. How about this? Step 2, take this equation and manipulate it to your liking and then pick k values. See, if I start picking k values now, I don't know what that really looks like in the xy plane. It looks complicated to me. But can you rearrange this? It's like, can I multiply 1 plus x squared plus 2y squared on both sides? They would look good. So I get 1 plus x squared plus 2y squared multiplied on this side, divide the k, I get 100 over k. That looks a little better. I don't want that 1 over here. I like to have my x squareds and y squareds on one side. So how do I get that 1 over here? 100 over k minus up 1. Now I like that. I know what these are. I know what these curves are. Think of this. This is just going to be constants. These will be constants on the right side. They're not circles, but they're what? Ellipses. They're ellipses. Very good, Channeman. They're ellipses. If it was x squared plus y squared, same coefficients in front of x squared and y squared, you got a circle. But this makes those ovals, where one's a 1 and one's a 2. So we're going to get a bunch of ellipses. We'll just sketch 3 of them, okay? Ellipses. I need you to help me pick. Well, it's a family of ellipses. Mathematicians use that word family. It's a family of ellipses. Help me pick some k values though. That was a good one. Now listen, let k equal 50. Alright, so if you let k equal 50, 150 is 2, 2 minus 1 is. That was a good one. That was a love it. Now, how do I sketch this? I use intercepts. We're going to sketch that daggone thing, and we'll put a 50 on it. What's going on at x equals 0? Ugh. Plus or minus 1 over square root of 2? That's okay. And what if y is 0? What do you get? Plus or minus 1. By the way, that number right there, you can hit a calculator. That work? Because y squared would equal 1 over 2. If I let x equal to 0, y squared would equal 1 over 2, but what would y equal? Plus or minus the square root of that, which would be 1 over square root of 2. You know, square root of 2 is like 1.4, so as long as we know this number is 1 divided 1.4, you know, it's going to be less than 1. But this will be at what? 1. So you can see which way is it more stretched. Right there at 1, but if I do a 1 here and a negative 1 here, I mean, does anyone want to hit on a calculator? What's 1 divided by 1.4?
4.
It's point something.
What? 1.5.
1 divided by 1.4. I'm just curious. 0.7? So I can go through these points, but it's like I'm kind of going through about 0.7-ish. Just to get a nice rough sketch. That's right. And I'm going to label it. What's the K value? 50. Isothermals. Oh, the temperature of the thin plate. Right there. Any point along here, the temperature is really hot. It's 50 degrees. Is this Celsius? They didn't say. All right. Hey, we need another K value. 20. I like that too. She goes, let K equal 20. I get x squared plus y, x squared plus 2y squared equals 4. Now let's sketch this. What's going on at x equals 0?
Plus minus root 2.
Okay, plus or minus root 2. What's going on at y equals 0? Plus or minus 2?
2.
2? Got the negative 2? But these, that's about 1.4. So 1.4 would be about right here. Negative 1.4 would be right there. It's not a circle, but it's an ellipse, isn't it? These are ellipses. Not circles, but ellipses. Because this is negative 2. And that's 2, so it went through there. And I'm going to label this with a what? 20. Hey, one more level curve. You all are good at it. K equals 10. I got enough of them right here. K equals 10. What do you get? X squared plus 2y squared equals
9.
9. So some intercepts. At 0, it's plus or minus, what would be that?
3 over root 2.
3 over root 2. And what if y is 0?
It's plus minus 3.
Intercepts get us out of anything. Ellipses, hyperbolas, Heck, even when we sketched that plane earlier. Here's my little curve. Well, this thing got up to 3, but then again, 3 divided by 1.4. I mean, that's closer to a 2, isn't it? Right? And I'll label it with a 1. And these are ellipses. So they're not circles, but they are ellipses. So can you make a rough sketch of this? All right, I'll just do here z-axis. I won't even draw the x and y-axis. Can you tell me what's going on? What's going on at a height of 10? There's a height of 10 on the z-axis.
That's the biggest.
Really wide, really wide. All right, so just gonna make a really wide, distorted looking ellipse. What's going on at a height of 20? Did it get bigger or smaller?
Smaller.
Okay, smaller, distorted. And what's going on at a height of 50?
Smaller.
10, 20, 30, 40, 50,
Smaller.
even smaller. There you go, just rough sketch. If you can go further, you can, you make a point. There you go. Good job with that.
Looks like an inverse square. Right.
Yep. And we're almost done with section 14.1, which mostly dealt with what? Level curves. What was the other topic? Domain and range. I mean, sometimes you just, at the end of the course,